Assalamualaikum and good day. In this video, we are going to talk about cloud chamber experiment. The cloud chamber is an early particle detector that makes radiation visible. It was invented by Charles Wilson in 1911. Inside, supersaturated alcohol vapor fills a sealed chamber. When a charged particle travels through, it ionizes the vapor, and tiny droplets condense along its path to form visible tracks. These tracks come from many types of particles. Primary particles include cosmic rays, alpha and beta particles. Secondary particles like muons, electrons, and positrons are created when primaries interact with air or the chamber itself. Each type leaves a different trail. Alphas are thick and short, betas are thin and curved, and muons produce long straight lines. Sometimes, high voltage is applied to remove stray ions, making the tracks clearer. Cloud chambers played a major role in discovering new particles and are still used today to demonstrate radiation in a striking visual way.
In a cloud chamber without an electric field, we can still observe the track of charged particle. We can identify different types of particle by looking at the appearance of their track. So firstly, alpha particle produce thick, short and straight tracks. They are heavy and highly ionizing, so they lose energy quickly and don't travel far. Next is photoelectrons, which are electrons knocked out of atoms by photons, create thin, wavy or scattered tracks. They are light, move faster, and are more easily deflected by collision with gas molecules. For positrons, the antimatter counterpart of electrons, leave tracks that look similar to electrons, which is thin and long. But without magnetic or electric field, we can't tell them apart since both make similar ionization patterns. So, even though there is no electric field, we can still detect the presence of radiation, see how often the particles appear, and get some ideas of the particle types and from how the tracks look. But we can measure the particle charge, energy, or the directions of motion.
While the observations made using the rudimentary setup was impressive, it was clearly limited in terms of qualitative analysis. To make a better comparison, we turned to a more elaborate cloud chamber setup with one key difference, being the presence of an electric field. This electric field helps separate ions, which improves visibility and results in longer-lasting tracks. Additionally, to assist in particle identification, we used RoboFlow YOLO, which is an application that can observe and determine the type of particle by the track it produces. We left the application running atop the cloud chamber for 5 minutes and analyzed the recorded footage. Over the session, we identified 3 types of particles: electrons, alpha particles, and a muon. At the time of recording, the alcohol vapor was already starting to thin, but the period of observation between each particle detection was small enough in time to make an accurate analysis. Electrons were the most frequently observed. They produced thin tracks, sometimes straight, indicating high energy, and sometimes curly, a sign of low energy and frequent scattering due to their small mass. Alpha particles, while less common, were easy to identify. Their tracks were thick, straight, and relatively short. Being heavy and strongly ionizing, alpha particles lose energy quickly and travel only a short distance. Finally, we observed what we believe to be a muon at the edge of the chamber, a long, straight, and relatively thick track. Interestingly, this track was not picked up by the application, but visually matched what we'd expect based on theory. Because muons are much heavier and more energetic than electrons, they penetrate further and scatter very little.